Hi, I'm here to talk about set builder notation today so that we can accurately understand it and use it to describe sets. So let's start with an example. I'm going to call this set A. A is the set of all n in the natural numbers such that n is odd. Set builder notation always has two parts, the left part and the right part, and separated in the middle by either a vertical line or a colon, which is two dots. The part on the left is called the expression. So that is the name that we temporarily assign to values to see whether or not they are in A. On the right, we have the condition. So the condition is the property that must be true if the value that's been assigned to n is to be in A. And then finally we have the universe. So that is the set of possible values that you're allowed to consider. So in this case, the only things that could possibly be in A are natural numbers. As an example, let's look at 4. Is 4 an element of A? Well, first of all, 4 is a natural number, so it is in the universe, which is important. So that means I'm allowed to even ask this question. So I imagine, okay, let's say that 4 is temporarily assigned to be equal to that expression n. Then this n over here on the right refers back to that n. So if this one over here is 4, then this one over here is also 4. And so that means that I'm going to look at the statement here now. 4 is odd. Is that true or false? I think we all agree that's false. And so the answer is no. 4 is not an element of A. Similarly, if I want to know is 11 an element of A, I imagine putting in 11 for that expression temporarily. Then if 11 is n over here in the expression, then I go to the condition and I say 11 is odd. True or false? That's true. So 11 is an element of A. Now if you think about it, the letter n did not actually matter there. When we were thinking about specific values like 4 and 11, it didn't matter at all that it was an n. I could have called it k. If I'd called it a k, and I imagine putting in the 4 for k right here, and the 4 for k right there, 4 is odd. That's the same statement I had before, and it's still false. So it doesn't make any difference. I could have called it r, and it would have been exactly the same thing. The actual letter name that we use there for the variable does not matter as long as here in the condition it's referring back to the right thing there in the expression. So we call that kind of thing a dummy variable. So that is called a dummy variable. It doesn't matter, you can change the letter into any letter you want. You can use t or epsilon or beta or anything. With one caveat though, let's say I put a k right here, and then over here on the right I say L. Then if I imagine putting in a 4 there and wanting to know is 4 an element of A, then I would come over here to the right and ask myself, okay, now put in 4 for k, and there is no k. It doesn't make any sense. And the statement as it stands, L is odd, I don't know if that's true or false because I don't know what L is. I have no information about L. So I cannot use an L like that there. I would be completely confused. I have to use the letter k there so that I'm referring back to the same k in the expression. Okay, now let's look at some other forms that these types of sets can sometimes take. So for example, I'm going to make a new set now called B. B is the set of all 3t minus 2 such that t is an integer. And let's say I want to know, is 19 an element of B? So remember that the expression for possible elements of B is 3t minus 2. So if I imagine putting 19 there for that expression, well that means that 3t minus 2, the entire expression 3t minus 2, should equal the value 19. And if I think about it a little bit, I can realize that yes, 19 looks like 3 times 7 minus 2, which means that the thing that's being placed in for t there is 7. Now, is 7 an element of z? Is this true right here? Yes, it is. It's an integer. And so I can say yes, 19 is an element of B because 19 has the form 3 times 7 minus 2, 3t minus 2, for a value of t that is in the integers. Similarly, is -4 an element of B? If I look at the value -4, and I imagine placing it in there for the expression, then that means -4 would have to equal 3t minus 2. And with a little bit of algebra, I can quickly see that the only possible answer to that equation is t equaling negative 2/3. If I put negative 2/3 there in the condition, then no, negative 2/3 is not an integer. So since the only value of t that could make the expression equal to negative 4, the only value of t that works is not an integer. And so therefore negative 4 is not an element of B. Okay, finally, let's just look at a couple more examples and think about how to list out all of the elements in a particular set. So here's an example. The set of all 2k minus 2 to the k minus 1 such that k is a natural number. So the elements here have the expression 2 to the k minus 1. And because the way the natural numbers are described, the natural numbers start with 1, then 2, then 3, the easiest way to write out this type of set is just to go ahead and start writing out the elements. 2 to the 1 minus 1, 2 squared minus 1, 2 cubed minus 1. Just go ahead and start listing them in order, starting with 1. And then I can do as many as I want and write dot, dot, dot. The dot, dot, dot at the end is showing that it keeps going, so that there are an infinite number of elements in this set. Another example might be the set of all x squared such that x is a real number. Now this one, I can't just start with the smallest real number and then go through them all in order, the way I could with the natural numbers. With the natural numbers, you can count 1, 2, 3, 4. With the real numbers, there are real numbers all over the place. There's no smallest real number, there's no largest real number. In between any two real numbers, there's always more real numbers, so they're not in a nice, well-ordered set. So instead, I just have to sort of imagine. So if I were to think of things that could be of the form x squared, could have that expression where the condition that would have to be true is that x must be an element of R. So for example, 9. Could 9 have this form? Could 9 be something squared? Sure, 9 is 3 squared. What about 32? Could 32 equal something squared? Sure, 32 is equal to the square root of 32 squared. Okay? So it seems almost like we could get anything then, right? We could just take the square root, except if we think about it a little bit more and maybe think about a number line and imagine the different values, what we can see is if I were to take something down here, no square number can ever be negative. So instead it's going to be just the values from 0 on up, just the non-negative numbers. So I can write it that way, 0 to infinity. Finally, 5j plus 1, such that j is an integer. So this is a little bit in between. The integers, if I just start with 1 and count up, that's not going to be quite right. But if I do start with 1, if j is 1, then 5j plus 1 would be 6. And if j were 0, it would be 1, so I can just list a few of them. But then I also have to sort of go backwards and think about some negative values of j as well, and then with the dot, dot, dot on either side to show that it keeps going in both directions. Okay, so hopefully these examples of set builder notation have helped you become a little bit more comfortable with it. And it's a really key topic that's going to come up again throughout all of your upper division math classes. So you want to practice it and make sure that you understand what all the different ways of writing it means.